So we're going to look at an example of how we come up with a matrix that represents a linear transformation from V to W. As we do that, we're going to have to simultaneously define what we mean by represents. So there's sort of going to be two things going on at once here. First, we're going to see how, starting with the linear transformation, how we come up with the matrix, and at the same time we're going to be describing exactly how it is that the matrix represents the linear transformation. So let's look at this function. So the function from P2 to R2 defined by this map. So f of a polynomial P is the vector in R2 whose first entry is P of 1 and second entry is P of minus 1. So just to have a concrete example in front of us, f of say x plus x squared is, right, to get the first entry, we plug 1 into this polynomial, so that's going to give us 1 plus 1 squared, that's 2. And then to get the second entry, we plug minus 1 into this polynomial, so that's minus 1 plus minus 1 squared, that's 0. Okay. We know that this is linear because each of these entries is an evaluation map, and we know that the evaluation maps are linear maps from any polynomial space to the real numbers. And it turns out if each entry is a linear map, then the whole thing is a linear map. You can check the details if you want. Okay, so how can we come up with a matrix? So remember, what we need to do at the beginning is pick a basis, because right, everything kind of depends on or a basis is how you come up with a coordinate system that lets you talk about a vector space. And also, a basis gives you a nice linear, or a nice isomorphism of a space with a Euclidean space. So let's choose some bases. For P2, we'll use the bases that we usually choose. So B, the basis B is going to be 1, x, and x squared. And for R2, we could use the standard basis, but for various reasons that would kind of obscure what's going on. So, because using the standard basis sort of is a special case. So let's avoid using the standard basis, and instead let's use the basis 1, 1 and 1, 0. Right? This is still a perfectly good basis. Maybe it's not the basis you would choose, but it's a perfectly good basis for R2. All right, so let's see how it is that these bases sort of produce a matrix. Okay. Now keep in mind as we do this that we have this function going from P to R2. We have P2, we have an isomorphism with R3 that's given by rep B. And for R2, we have an isomorphism of R2 with R2 given by rep D. Okay? And what we're going to do is fill in the gap here by figuring out some matrix. And when we do this, we're going to have to A, figure out the matrix, and B, figure out how is it that a matrix produces a linear map from R3 to R2. So, and we'll do both things at once. All right, so what we're going to do is start with our basis elements, and we'll ask the question, so for each basis element, 1, x, and x squared, we know we can write f of each basis element in terms of D, in terms of the basis D, right? And the coefficients will, if we just pick off the coefficients of these representations, the coefficients will give us the result of rep D on f1, fx, and fx squared. Okay, so let's do this, and then we'll see sort of how this does what we want to do. So what we're going to do is for each basis element in P2, we're first going to do F, which gets us to R2, and then we're going to, by writing the result in terms of the basis D and pulling off the coefficients, we get the result of rep D on that vector. Okay, so let's actually do this. So what we're going to do is first compute f of 1. Okay, so the polynomial 1. So what happens to the polynomial 1 if you evaluate it at 1? You get 1. What happens to the polynomial 1 if you evaluate it at -1? You get 1. Right? The polynomial 1 just always gives you 1. Okay, now we need to figure out what rep D, right, so now we're up here. To figure out what rep D does to this vector, we have to write this vector in terms of the vectors in terms of the basis vectors in D. So this is 1 times 1, 1 plus 0 times 1, 0. Okay, so now rep D of f of 1, right, so we're taking the result of f of 1 up here, and we're hitting it with rep D, which takes us down to R2. So rep D of f of 1, it just pulls off these coefficients and makes a vector out of them. So 1, 0. Okay, so rep D of f of 1 is 1, 0. So to record that, let's write those right there. Let's write these coefficients right here. So this was our first basis element, our basis element 1, and by doing f and then rep D, these are the coefficients for our first basis vector 1, 1, and the coefficient for our second basis vector 1, 0. So what this column is describing is what coefficients on the basis D do you need to describe f of this basis element in P2. Okay, well now we can do the same thing for f of x, our next basis element. So we're figuring out for the basis element x, when you hit it with f and then do rep D, what are the coefficients that you need to write f of x in terms of these basis vectors. Okay, so what is f of x? Remember, f is the function that plugs 1 into this polynomial, so that gives you 1, and then plugs -1 into this polynomial. That gives you -1. Now we need to write this vector in terms of the basis D, right, which was 1, 1, and 1, 0. So to do that, we're going to need, I think, -1 times 1, 1 plus 2 times 1, 0, right? You can check that this all adds up. Okay, so what does rep D do to this? Sorry, this shouldn't be a 1, this should be an x. Rep D just pulls off these coefficients, so -1 and 2. So in the column for our matrix corresponding to the basis element x, the coefficient for the basis vector 1, 1 is -1, right, from here, and the coefficient for the basis element 1, 0 is 2, right? And this is because f of x is equal to -1 times the first basis vector plus 2 times the second basis vector. Okay, now we only have one more basis element to go, and that's x squared. So f of x squared is, remember we plug -1 into here, that gives us, sorry, plug 1 into here, so 1 squared is 1, and then plug -1 into here, -1 squared is 1. Write this in terms of the basis vectors in D, so we get 1 times 1, 1 plus 0 times 1, 0, and then rep D of f of x squared pulls off these coefficients, so 1 and 0. So in this, our last column, so for the column corresponding to the basis element x squared, the coefficient for f of x squared for the basis element 1, 1 is 1. And then the coefficient for f of x squared for the basis element 1, 0 is 0. Okay. All right, so this is our matrix, right? And the general process for any linear map will work the same. We'll have a column for each basis element in our domain. We'll have a row for each basis element in our range. And the entry in each spot tells you the coefficient for that basis element, the coefficient you need on that basis element in the codomain to describe f of that basis in the domain, right? Okay, so that describes how we're getting this matrix. And just to give this matrix a name, for now we're going to call this A. Okay, but what we need to do now is see how it is that this matrix A describes a linear map from R3 to R2. And we need to do it in a way, so to sort of keep everything in sync here, we need to do it in such a way that if we start with a vector in the upper left here, or a polynomial, doing f and then rep d gives us the same thing as if we do rep b and then hit it with the matrix A, whatever hit it with the matrix A means. So to see how the matrix A is supposed to affect a vector in R3, let's see what happens if we start with any polynomial and go right and then left. And then we'll compare that to going down and then right. Okay, so if we start with any polynomial, that would be A times 1 plus B times x plus C times x squared. So what does f do to this? Well, we could plug in values to see what f does to this, but we know f is a linear transformation or a linear map, so we might as well use the fact that f preserves structure. So this is A times, right, f sends 1, right, we've computed f of 1. F of 1 is 1, 1. Right, so here's f of 1 plus b times f of x, which was 1 minus 1, plus c times f of x squared, which is also 1, 1. Okay, now we'll see what rep d does to this thing. So rep d of f of a plus bx plus cx squared. Okay, well, to know, actually maybe we should wait to do this for a second. To know what rep d does to this, first what we need to do is write each of these vectors in terms of the basis vectors in R2. So 1, 1 was 1 times 1, 1 plus 0 times 1, 0. Right? So I'm using square bracket. I should use parentheses here. Okay, plus b times, now write 1 minus 1 in terms of our basis vectors for R2. So this is, we said it was 1 times, sorry, minus 1 times 1, 1 plus 2 times 1, 0, right? That is what we said? Yes. Okay, plus c times, and now write 1, 1 in terms of the basis vectors, which we already know how to do. So this is 1 times 1, 1 plus 0 times 1, 0. Okay, now we can multiply all this all out and group them according to which basis vector appears. So if we look at all of the terms that are multiplying the vector 1, 1, let's see, there's a 1 times a, there's a minus 1 times b from this part, so minus b, and then there's a 1 times c, so c, so plus c. So a minus b plus c times 1, 1, plus, and now all the terms that come from 1, 0. So what are the terms coming from 1, 0? Well, there's a 0 times a, right? Plus, and then here's a 2 times b, and then 0 times c. Okay, so that's equal to this. So what does rep d do to this? Rep d of f of a plus bx plus cx squared. Rep d just pulls off these coefficients, right? So this one is a minus b plus c, and this one is 0a plus 2b plus 0c. So you might be wondering, why am I writing 0a? Couldn't I just leave that off? Yes, but there's a reason that I want to write it. So now notice that if you look just at the coefficients of a, b, and c here, if we write down the matrix just of the coefficients, we get 1, minus 1, 1, and 0, 2, 0, right? Which, that's exactly what we got for the matrix A. So, right, here's the matrix A again, right? So maybe this is a hint that this matrix A really does represent something essential about the linear map F. Okay, so remember, the reason that we were calculating this was because we wanted to know what should the matrix A do to a vector in R3. And we're going to cook things up so that if you start with a polynomial in P2 and you do rep B and then you do A, whatever doing A means, you should get the same thing as if you start with your polynomial, do F, and then you do rep B. So we've rep D, sorry. So we've just figured out what happens if you start with a polynomial, you do F, and then you do rep D, right? If you start with a polynomial, this polynomial, you do F, and then you do rep D, this is what you get. So this should be the same thing as starting with the polynomial, a plus bx plus cx squared, then doing rep b, then doing the matrix A. And again, I'm being vague about what doing the matrix A means because we haven't decided what that should mean yet. Okay, but we do know that if you do things in this order, you should get the same thing, right? So, what is the result? Well, first let's figure out what rep B does to these things. Well, right, B is the basis 1, x, and x squared, so rep B just pulls off the coefficients from 1, x, and x squared, right? Rep B pulls off the coefficients for when you've written things in terms of the basis, so A, B, C. Right, so now we come to defining what should A do to rep B of A plus bx plus cx squared. Okay, so what we're really defining here, right, this rep B, this is what we just calculated. What we're defining is what should A do to the vector ABC. And remember, we don't have any choice. We have to define the operation of what the matrix does by saying it has to be equal to this, right? We don't have any choice. So this has to be equal to make this square up here come out right, so that going both ways gives you the same thing. Matrix A somehow applied to the vector ABC has to give us this right here. So A minus B plus C, and then the second entry 0 times A plus 2 times B plus 0 times C. Okay. Now this is really a definition, right? Remember, we were doing this whole thing to decide what should it mean for A to do something to a vector in R3. So our matrix A was 1, minus 1, 1, 0, 2, 0. We were letting it do whatever it's supposed to do to A, B, C. And the result that we have to get for everything to work out right is A minus B plus C and 0A plus 2B plus 0C. Okay, so essentially the operation that's happening here is we're taking this vector, kind of turning it sideways above the matrix like this, and then we sort of slide downwards, and every time we hit a row, we multiply and add. So when we slide these A, B, and C down to this row, we get 1 times A minus 1 times B plus 1 times C, so that's this. And then when we slide A, B, and C down to this row, we get 0 times A plus 2 times B, right, plus 0 times C. Okay. So this is how this matrix acts on R3. And with this definition, we have explicitly made this definition so that starting with a polynomial and going this way is the same thing as starting with a polynomial and going that way. Right? And generalizing this to other maps and other vector spaces will be how we translate, or how we translate a linear map into a matrix that represents this linear map. So we'll use this translation process, but also we will use this meaning for what we mean by A represents the linear map.